Hello, everyone. Today, we are going to talk about simplifying rational expressions using the method of factoring. Our objectives is to be able to simplify rational expressions using factoring. You should be able to multiply rational expressions. That you can determine the value where x is undefined in a rational expression. All right. So let's go through what a rational expression is. A rational expression is one where two polynomials are in the form of a fraction. So I'm dividing a polynomial over a polynomial. One in the numerator, one in the denominator. We were working with rational expressions that were monomials. We had a monomial over a monomial, and we used the method of the rules of exponents to simplify that rational expression. Well, now we're going to look and we'll notice that we have a binomial or a trinomial in the numerator and denominator of a rational expression. We cannot use our exponent rules. We have to factor first, okay? We got to factor and then we're going to cancel common factors. So here where it says the key to simplifying rational expressions is to be able to, what we are going to say is we need to be able to factor. That is the key. So let's take a second and let's go over our different factor patterns. All right, let's review the factor basics. So the first factor pattern that we went over was the GCF method, and that's where we looked at a polynomial and we looked at the coefficients. We decided what number could divide evenly out of those coefficients, right? If I look at this term, 3x squared plus 15x, looking at the coefficients, I notice I can take out a 3 out of the coefficients. Now, if I look at the variables in a polynomial and they share a common variable, I can take out a GCF of a variable with the lowest power. In this case, I'm taking out an x to the first power. So my GCF is 3x. And then what I do is I write my GCF in the front of the parentheses, and of course we leave in what we're left with when we divide each term by the GCF. I would be left with ax plus 5. All right. Now, let's look at the next factor pattern, difference of squares factoring. I look at difference of squares. I know that happens when I have two perfect squares. It's a binomial, so I see two terms. They're perfect squares, and I'm subtracting. I know I'll use that difference of squares factoring, which means that I take the square root of each one of those terms and I put it in a plus minus factor, okay? So in this case, the square root of x squared is x, and the square root of 4 is 2, right? So I know my factor would be ax plus 2 and an x minus 2. The next one is product sum method. The product sum method is doing exactly what it says. I am going to look at the polynomial. I use this method when I see that it is a trinomial, okay? There's 3 terms. I look at the constant term in the back, and I think of what two numbers multiply to be the constant term and what number adds to the middle term. In this case, I need two numbers that multiply to a negative 15 and adds to a 2. So my two numbers I'm thinking of is 3 and 5. And because I wanted to add to a positive 2, I know it's going to be ax plus 5, ax minus 3. All right. Let's look at our last factor pattern. We have bottoms up method. This method is when you see the trinomial, but in this case we have a leading coefficient. I call this method bottoms up because what Miss Bennett likes to do is kick that leading coefficient to the back. Bye-bye. All right, so I kick it to the back by multiplication. So I end up with ax squared minus 7x minus 18. Okay, what I like to do at this very moment, all I'm doing is I'm getting rid of that leading coefficient, rewriting the problem so it looks like product sum. Then I just do the same thing that I'm used to. I'm going to think of two numbers like product sum that multiply to this number back here, the negative 18, add to my middle term, the negative 7. And in this case, our two numbers, I can change the color. Let's go with pink. All right, so our two numbers in this case would be 9 and 2. Okay, because I wanted to add to a negative 7, I'm going to say the factor is x minus 9, x plus 2, and I'm not done here. Okay, I got one more step. Because I kicked out my leading coefficient in the beginning, that means that I have to recognize that that's my last step. I have to recognize I did that by dividing that leading coefficient out. I got to divide it out of these two numbers. So I'm just going to divide by 3 here. All right. I divide both of those by 3. And then the last step is just to simplify my factors if I can. Miss Bennett's going to go ahead and write the end result up here. The first factor, x minus 9 over 3, that simplifies to ax minus 3, right? 9 over 3 is just 3. The next factor, if I can't simplify that fraction, so this is where we get bottoms up. We take everything in the denominator and move it on up. Move it on up. There we go. So that factor would turn into a 3x plus 2 bottoms up. All right, 3x plus 2. Let's look at our combination. We're going to put all the factoring together and see what we got. So for the combination method, if I look at this one, the first thing that I'm going to do with this binomial is just take out a GCF because that's all I'm seeing right now. I notice both of them are divisible by 2. So 2 is one of my GCFs. And they both have an x in it. So I go for the x with the lowest power. That's x to the first power. Now, what would I be left with when I divide by 2x? Well, if I look, I would be left with a x squared minus 9. And I'm looking at that factor x squared minus 9. I realize I can factor more, right? That's my difference of perfect squares. So I know my final factoring is, I'm going to write it over here, it would be a 2x times x minus 3, x plus 3. All right, this last one says combination. We can go ahead and X that out because this was not a combination problem, and that's due to how this was printed, okay? You can't do multiple methods of factoring on this problem. You can only do one. If you look at this, the only thing we can do is take out a GCF, right? The only thing we can do is take out a 4 as our GCF. Let's think about what we're left with once we take out a 4. Well, we're left with a x cubed minus 7x squared plus 12. All right, x cubed minus 7x squared plus 12. All right, guys, let's move on. Let's move on. All right, so now that we warmed up with all of the factoring, we're going to use this same method to simplify the rational expressions by factoring each part, the numerator and the denominator. And then the next thing we're going to do after we factor the numerator and denominator of the rational expression is we're going to cancel out common factors from top to bottom. Let's look at this example that they give us. We have a x squared minus 4 over a 2x cubed minus 4x squared plus 5x minus 10. All right, I see this and they tell me to simplify the rational expression. I'm first going to factor the numerator. I factor the numerator using my difference of squares method, which is x minus 2 times x plus 2. In the denominator, I do the same thing. I'm going to factor this using the GCF method, grouping. I'll group together the first two terms. I'll group together the last two terms, right? And I'll just take the GCF of each term, each of the two terms separately. So my first group, the GCF for this is 2x squared. And let me get another color. I'm not liking this blue. Let's go for a red. Okay, so it's 2x squared. And then what would be left would be a x minus 2. My second term, I could take out a 5. What would be left is an x minus 2. Now, I know between the two sets, I've created two terms, right? And both of them have an x minus 2 in common. So that's the GCF between those terms. So I know that when I factor this, that is my first factor, what they have in common. Okay, so it is the x minus 2. That's one of my factors. And then my next factor, I regroup what's left over. What's left over is the 2x squared and the plus 5. There we go, plus 5. There we go. All right, guys, if I'm looking, I'm going to cancel. I'll do my last step. I cancel common factors from top to bottom. Okay, so we look at this and we see that those x minus 2's cancel from top to bottom. And what we would be left with is the x plus 2 over 2x squared plus 5. Okay, let's look at the next one. I want you to go ahead and try this. Pause the video. I want you to simplify this rational expression by factoring first, then cancel common factors. Don't think too hard. Look at the numerator and look at the denominator. We just saw these polynomials earlier. Simplify this rational expression. All right, is this what you got? We grabbed the factors that we just did. I know 3x squared minus 7x minus 6 factors to 3x plus 2 and x minus 3. The denominator here factors 2x plus 5, x minus 3. And look at this. We're going to cancel common factors from top to bottom. Cancel those common factors. We would be left with a simplified factor of 3x plus 2 over x plus 5. Okay, let's let's take a second and talk about why this works, all right? What I want you to do is I want you to use your methods of multiplying fractions, and I want you to go ahead and multiply this fraction out. Now remember, when we multiply fractions, we multiply across numerator times numerator, denominator times denominator. If we look at this fraction, if we multiply straight across, we would end up with a 60 over a 200 a 252. All right, 60 over 252. Notice that that fraction is not in simplest form, right? I would have to reduce this fraction to get it in smallest, simplest form, all right? But look, let's do something before we reduce it out, okay? Because we could go ahead and start reducing the factor to get it in simplest form, and we'll do that in a second. Let me use my method that I used up here. Let me write out all the factors, okay? So I'm going to write all the factors of the numerator and denominator, and I'm going to cancel the common factors from top to bottom and see if I can automatically get this in simplest form when I multiply. So let's see. If I go ahead and do that, I look at the 4 and I write all the factors of 4 in the numerator. Well, the factors of 4 is 1 times 2 times, I hate how it writes my twos. There we go. 1 times 2 times 2. If I look at the numerator of the other fraction, 15, and write all the factors, well, that's 1 times 15. Or times 3, times 5. So 1 times 3 times 5. Uh-oh. I want this to be a 3. There we go. Times 5. All right, 1 times 3 times 5. In the denominator, I can rewrite the factors of 9. Well, the factors of 9 is 1 times 3 times 3. And 28, I'll write all those factors out. That is 1 times 7 times 2, there we go, times 2. All right, so there are my factors, and I cancel common factors from top to bottom. Well, I start canceling out the common factors. I'm going to cancel these ones. The ones have to go. I cancel my 3 from top to bottom. Look, I got 2 2's in the numerator, right? And I got 2 2's in the denominator. So what I'm left with in the numerator is the 5. And in the denominator, I'm left with a 3 times a 7. And notice that's just 21. So this simplifies to 5 over 21. Notice how I did it. I got the fraction in simplest form immediately. I was able to simplify this by using that method of expanding all the factors and canceling the common factors out. It works because it has always worked, okay? This is what we have been doing to simplify fractions since the beginning. We look for common factors. We reduce the fraction by taking out the common factors, right? If I simplify this over here, I would just look for the common factor between 60 and 252, and I start dividing them out. I get rid of them until I have the simplest form. Same thing over here. That's what we do. Now, this is something else that we need to watch out for. As we're simplifying common factors from top to bottom, and we start canceling things out, we cancel those common factors out, we need to make sure we watch out for the missing factors in the numerator, okay? And the missing factors in the denominator, we need to make sure we understand what that means. So if I look at this case here where I have a 5 over 5x, I know that I can go ahead and cancel out these 5's, right? They're both the same. Well, I notice now there's nothing in the numerator and there is a x in the denominator. So my question to you is, if there's nothing in the numerator, does that mean it's a 0 in the numerator over x? And my answer to you is no, absolutely not, okay? When we're talking about division, canceling out or having same over same, that means 1, okay? So this is not correct. I want you to put a big fat X in that, and no, I'm not going to be tricked. If I cancel out and it's nothing left, I am not left with a 0. I'm left with a 1, okay? So the correct answer for this would be a 1 over x. All right. Okay, let's look at example A. They asked us to simplify this rational expression. We will do so by factoring. The first thing I'm going to do is look in the numerator. I will factor out the numerator using my GCF method. I know that I can take out a x from that x squared plus 5, and I would be left with a x plus 5. In the denominator, I can't factor x squared, but I can go ahead and expand it. I can write it as x times x. Now I notice the common factors that I can cancel out. From top to bottom, the x's go away. I'm left with a x plus 5 over x. That is the simplified version, x plus 5 over x. In example B, I need to go ahead and simplify this. I'm going to do it by factoring first, both numerator and denominator, then I'll cancel out common factors. I notice in the numerator I can factor it by taking the product sum method. This is x plus 1, x minus 6, right? Two numbers that multiply to a negative 6 and add to a negative 5. In the denominator, that looks just like my difference of squareds method. So I know my factor pattern is the square root of both of those terms, and it's the plus minus factor. So I should have a x plus 1 times x minus 1. Now, to simplify this rational expression, I am going to cancel out common factors from top to bottom. So my factors cancel, the x plus 1 factors cancel. I'm left with a x minus 6 over a x minus 1. My next example is a little bit different. Guys, if we go back to our objectives, today we are learning how to simplify rational expressions using the factor method. The next thing we're going to learn is how to multiply rational expressions. And that is something that they're asking us to do in example C. We're going to multiply rational expressions no different than we did with our fractions. We'll multiply across numerator times numerator, denominator times denominator. And what I told you all to do, or what I told you to think of though, when you're dealing with rational expressions and you're talking about multiplying them, when you think multiply rational expressions, you're going to think of factoring than smushing. Factoring and smushing. And what Miss Bennett is saying is she wants you to factor everything out and then just smush everything together. And you are seeing that smush motion that I taught you right now as I say that. So if I look at example C, I look at the first fraction, x minus 3 over x plus 2. I cannot factor that, okay? So that is what it is. But if I look at the second rational expression, which is a x squared plus 5x plus 6, right? I can factor that. The numerator factors out to an x plus 2 times an x plus 3. If I look at the denominator factors out as well. This is our difference of squares method. It would factor to an x minus 3 and an x plus 3. Well, I factored everything out. Now my next step is to smush everything together. That's all multiplication of rational expressions is. You factor, then you smush. So I'm going to smush everything in the numerator together as one super huge fraction. So I'm going to use another color. I'm going to smush this all together. In the numerator, I'll have this x minus 3 times the numerator of the other rational expression, x plus 2, times x plus 3. In the denominator, I'll have x plus 2 and I'll have the denominator of the other rational expression, x minus 3 and x plus 3. I factor and then I smush, right? Factor and smush. So after I factor and smush, I'm just going to cancel. I'll simplify all of this by canceling common factors. Well, the x minus 3's cancel, the x plus 2's cancel, the x plus 3's cancel top to bottom. I noticed this was a big fancy way of just writing a 1. All right, let's go on to example D where they asked us to factor and smush. Okay, example D has us multiply the rational expression. And again, when I see multiplying rational expressions, I think I'm going to factor and then I'll smush everything together. Now, I look at the numerator of the first rational expression. I notice it is not in standard form. Already, Miss Bennett wants to rewrite this rational expression in standard form. The reason being is I just don't want to make any type of mistakes when I'm factoring. So I'm going to write that in standard form. I change the terms around. I write that x squared and I put it in the front so I don't make any type of factoring mistakes. Okay, now I'm factoring and smushing. Here we go. I know for the first rational expression, I can factor the numerator by taking out a 2x, and I'm going to take out a negative 1. I'm going to take that negative out as well. So I'll take a negative 2x out, and that would leave me with a x minus 2. Okay. The denominator of this rational expression simplifies. This is similar to the one we just factored, right? Except this is the minus factor. This would be product sum, and it simplifies to an x minus 3, x minus 2, right? X minus 3, x minus 2. And then if I look at the other rational expression, the numerator simplifies, to a x minus 1 and an x minus 3. Okay? If I look at the denominator is just 2x, right? I can't do anything with that. Now, I factored everything. It's time for me to go ahead and smush. Okay, so I'm going to put everything together. In the numerator, I'm going to put all of that together. The 2x, the x minus 2, okay, times the x minus 1, times the x minus 3. In the denominator, I'll put together everything in the denominator. X minus 3 times x minus 2 times my 2x. Okay, now that I've smushed everything together, I can go ahead and simplify. I simplify by canceling common factors. So these x minus 2's go away. The x minus 3 from top to bottom goes away. I can cancel out the 2x, okay? Now, what I'm left with, and I gotta be careful here, I'm left with this negative. I'm left in the numerator with this x minus 1, all right? So this all simplifies to a negative x minus 1, okay? Or this could be a negative x plus 1, all right? Either or is acceptable. Now, let's look back at our affirmation statements and see what else we have to learn. The last thing that we want to focus on is we want to be able to, we want to tell ourselves that we're able to determine the value where x is undefined in rational expression. Okay, so let's look back at the bottom of the paper and let's talk about the values when x is undefined. Okay, if we talk about the values where x is undefined in a rational expression above, we need to remember some things about fractions. Okay, in fractions, we cannot have a denominator equal to 0. Okay, we can never have a 0 in the denominator. That means the fraction is undefined. Okay, you'll get error, this can't happen. The same with rational expressions. So to find all undefined values, okay, of x for rational expressions, we will take the factors in the denominators and set them equal to 0. And we'll solve for x. Okay? And we're just thinking in our head, this is the zero product property. Okay? As long as I have all multiplication with my factors, I can set them equal to 0 and solve for x. We'll use this method to figure out when our rational expressions are undefined. So here we go. Let's go back to the examples in the beginning and let's figure out all the undefined values. So if I look at example A, and I'm told to find, I'm going to snip this, I'm told to find all the undefined values in example A, I'm going to look at the denominator in example A. I'll set that factor equal to 0 and solve for x. And let me go back. I'll look at the denominator when this thing was first simplified, or before it's simplified. So always look before you simplify, before you cancel anything. So that's over here. Our denominator was x squared. So I'm going to take x squared. I'll set it equal to 0. I'll solve for x. Well, the only thing that we can do is get rid of the square root, right? Or get rid of the square on this by taking the square root of 0. No matter what, guys, we would end up with x equaling 0, okay? The only thing that can make an x squared equal 0 is 0. X equals 0. So with that being said, we know the undefined value for this is at x equals 0. Okay, that is when this rational expression is undefined. Okay, it's undefined. So we cannot have x equal 0 because we would have a 0 in the denominator. So that's my undefined value. I take the denominator, set it equal to 0, solve for x. Let's go to example B. I look at example B and I go where right before I simplified. Okay, so I'm looking at the factors before I simplified. Okay, so my factors were x plus 1 and x minus 1. Okay, to find my undefined values, I need to set both factors equal to 0 and I need to solve for x, right? So I am going to set x plus 1 equal to 0. I solve for x. Well, that's just easy. I subtract 1 on both sides. The ones cancel. I'm left with a x equals -1. So at x equals -1, that's one place where my rational expression is undefined. I look at the denominator. I do the same for the other factor to find the other undefined value. X minus 1. I set that equal to 0. I solve for x. It's going to tell me the undefined value. That means I have to balance this out by doing the inverse. I need to add 1 on both sides. And I end up with x equals +1. Okay? So here's my two places where the denominator is undefined. Okay? I took the factors, set them equal to 0, I solved for x. At x equals -1 and at x equals +1, those are the places where that would give me a 0 on the denominator. That is where the rational expression is undefined. Okay? Let's go to the example C, the next one. Again, we're looking at example C before we canceled out anything, okay? We want to get all of those factors in the denominator. So I'm going to look at example C right here, okay? I look at every single factor in the denominator. I'm setting every single factor equal to 0, and I'm solving for x. First factor, x plus 2, all right? I set that equal to 0. I find the undefined value by solving for x. Well, I can just subtract 2 on both sides, right? I know that my answer here, my undefined value, is at x equals -2. I have another undefined value from this factor. It's at x minus 3. I set it equal to 0, and then I solve for x. I'm going to add 3 to both sides, get x by itself. I know the other undefined value is at x equals 3. If we're seeing a pattern here, then you are good to go. If you notice, hey, the undefined value just ends up being the opposite of the sign that's in the factor, you're good to go. You can go straight to the answer. If you already know, okay, at this other factor here, I know the undefined value is going to be a x minus 3, then that is okay. You can go straight to that undefined value. If you know that you need to do the work and you need to set each factor equal to 0 and solve for x, by all means, do that work so you know where the undefined values are coming from, right? They come from the factors of the denominator. We're just solving for x using the factors of the denominator. That's telling us where all of our zeros are, okay? So for this expression, the zeros are x minus 3, x plus 3, and x equals -2. Those are the undefined values. Now, we're going to move on to example D. I want you to tell me what you got. Pause the video, try to find the undefined values in example D yourself, and then check your work. All right, did you get the undefined values of 3, x equals 3, x equals 2, and x equals 0? If so, give yourself a pat on the back. You got it. If not, let's look at what happened. Notice what we're doing. We look in the denominator of the of the expression before it's simplified, okay? So if we look in the denominator, it's this part right here. We're looking at every single factor in the denominator, x minus 3, x minus 2, and 2x. We set each one of those factors equal to 0. Do you see that we did that over here? And we're going to solve for x, isolate x by itself. Those values are our undefined values or our restricted values. Now, guys, I want you to take this knowledge with you. Go to Khan Academy and do well. All right, I will see you tomorrow.